NaCl, and you're going to transfer that sodium and chloride into water. Okay? So we need to think about, is this favorable or is this not a favorable process? And we know that salt dissolves in water, right? So this is probably favorable. Will dissolve. So what do you think the dielectric constant of sodium chloride is? So a piece of salt. What's that? Is it 0, 1, 100? Let's see. Is it 0?
No.
No. What's the speed limit for dielectric constant?
1.
1. That's the lowest it can get, right? We always call water a high dielectric constant medium. Have we talked about any materials that have a higher KD? There aren't many, right? So what do we think the dielectric constant of sodium chloride is going to be? Just if we had to make a wild guess. Somewhere between 1 and 78, right? I don't know what it is, maybe 10? It's probably higher than that because there's a bunch of ions in there. Probably depends on temperature. But we know that sodium chloride will dissolve in water. So what's the sign of delta G for that process? Negative, right? Okay, so now we can go back to the equation and we can look. We can say, okay, I know this Born energy or this chemical potential here is going to be negative, right? Delta G is just delta mu on a molar basis. And so I can figure out what the sign of my dielectric constant is going to have to be, or my dielectric constant change is going to have to be based on this equation right here. And so if you look at this bottom line, so we're on the slide that says self-energy or Born energy of an ion, we see that the delta G for moving 1 mole of ions from gas to water is a gain in free energy, or is a delta G that's negative 1,000 kilojoules per mole. So this is favorable, thermodynamically favorable. And so the best way to think about how Born energy relates to solubility is thinking about, does the ion prefer to be in water, or does the ion prefer to be in whatever other medium it could be in? Or we think about our ion trying to make a decision, right, between water and vacuum. Where's the Born energy higher for this ion? In vacuum or in water? Vacuum, right? Born energy is proportional to 1 over kD, right? So if you put the ion in the vacuum, the Born energy is high. If you put the ion in water, the Born energy is low. And so things will want to go to the lower energy state, and we know ions like to go into water. So, bless you.
Thank you.
So we can think about this Born energy and solubility in a very simple way. That higher dielectric constant media are more soluble, or ions are more soluble in high dielectric constant. Ions are less soluble in low dielectric constant. So let me just write this out. Ions are more soluble in high Kd solvents. And then we can put where delta W, or Born energy, or self-energy is low. And so this is described, if you keep going on these slides, and you work through the derivation and all that stuff. This is shown exactly by this plot right here, where we have log solubility is related to 1 over the dielectric permittivity or the dielectric constant, right? Things are more soluble in water, and they're less soluble in propanol. Yes?
So I'm just trying to make sure I understand this. So the electrons are trying to get to the lowest energy state and the lowest Bourne energy, so they try to go to the medium with the highest dielectric constant?
Yeah, so the Bourne, I mean, they're not trying to get to the lowest Bourne energy. The Bourne energy just is what it is, and the equation for Bourne energy has dielectric constant in the denominator, right? So that's why the lowest Bourne energy turns out that provides the highest solubility because of the inverse relationship with dielectric constant. So it costs you, you have to, if you want to put this charge into a vacuum, it costs you energy to do that. Versus if you want to put a charge into water, that doesn't seem very hard at all, right? And so processes that require more energy are more difficult. So the most important part about this is what I just boxed right here. Ions are more soluble in high dielectric constant solvents. And so this table, transferring ions between vacuum and water, we've talked about that example a couple times, and so that'll be good to remember. And also this plot right here where we plot solubility as inversely proportional to dielectric constant or dielectric permittivity, right? This could be 1 over epsilon because we know they're the same thing, or 1 over polarizability. There we go. That's the alpha. So make sure that you remember these relationships as well. So if I tell you about the polarizability of a solvent, you might be able to tell me if ions are more or less soluble in it, right? Or if I tell you about the dielectric permittivity of a solvent, something like that. Yeah?
So I'm still a little confused. What's the difference between the vacuum and the water? Like why is it moving more towards the water?
So remember, vacuum has a dielectric constant of 1 or dielectric permittivity of 1, right? Water has a dielectric constant of 78 or a dielectric permittivity of 78. And so when we look at this simple equation right here, this delta G, and we figure out the sign of the delta G where we transfer the ion between a medium of KD1, so this is one dielectric constant, this is the other. So if we put 1 here and 78 here, this sign's going to be negative, right? But if we put 78 here and 1 here, this sign is going to be positive. And so things that have a negative delta G want to happen, right? So this ion wants to go to the high dielectric constant. So it's something, it's got deep fundamental basis in this Bourne energy, how much energy it costs to make the ion in a certain dielectric constant medium. But the thing to remember is this equation right here, or this equation, what's the sign of delta G? And just the table, right? So vacuum, where's vacuum on this table? Let's see, 1 over 1 is way out here at 1, right? So is the solubility in vacuum high or low?
Low.
Super low, right? There's hardly any. What's that? Oh. And high dielectric constant is way up here. So it's really, the reason that the ion wants to go into the water is because of the high dielectric constant. That's why it wants to go there. Yeah?
Kind of jumping back to the homework here.
Sure.
The question, number 4 question was talking about hydrated radii.
Mm-hmm.
What exactly is going on with that? I understand the hydration numbers of how it operates, but as far as the hydrated radii itself, we're confused on.
What's the question? Can you just read the question?
Yeah. In water, lithium and cesium have a similar hydrated radius. Please explain what's
Sure.
going on with the hydrated radius.
Sure. So do you know what a hydrated radius is?
Partially.
Okay, so all the hydrated radius is just the radius. It's lithium and cesium, right?
Yes.
What's bigger? What's the bigger atom, lithium or cesium?
Cesium.
Why? It's got way more electrons, right? And then so we can look at our periodic table. Oh, there it is. We can look at our periodic table, and cesium has 56 electrons, and lithium's only got 3, right? And so when we put an ion into water, lithium's got 55 electrons, because this is going to be cesium plus. Lithium only has got 2 electrons. And so now we start to put water around these guys, right? Because a positive charge really doesn't like to live on its own. A positive charge will be attracted to negative charges. And we know that water has a dipole, right? So we get partial screening of these positive charges with these negative charges. And so what's the magnitude of the charge on lithium? 1, right? What's the magnitude of the charge on cesium? 1. They've got the same charge. Cesium's bigger, and so if you take this little piece of cesium, it's got a lower charge than this little piece of lithium, right? So we could talk about the charge density which is the charge divided by the size. So is the charge density of lithium high or low? High, right? The size is small, this number is going to go up. So the charge density for lithium is high, so it's going to have more waters stuck around it to shield that charge. Whereas the charge density for cesium is low, and so it's going to carry less water around it because you don't need as many water dipoles around that ion to screen the charge. And so if you look at the bare ionic radii, lithium has a bare ionic radius of 0.068 nanometers. Cesium has a bare ionic radius of 0.169 nanometers, right? Just based on the number of electrons. And the hydrated radii are similar, which tells you that there's a lot more water around lithium